Everything
came from them. So
Yeah.
what is our two-ish?
I literally gave it to you totally wrapped.
All right, we gotta get moving here, folks.
That doesn't
Come to my attention all the time, so we need to move. So let's take a look
It is sour, bro.
at our notes. We may be doing a little skipping around here, but let's take a look at our notes. And it says the half-life of a certain radioactive substance is 20 days, and there are 5 grams initially. Find the time when there will be 1 gram of the substance remaining. Now, I need you to reassure me that you know what we mean by half-life. What do we mean by half-life?
the amount of time
Half-life, first of all, is a time.
it takes for a substance to degrade halfway.
Yeah, so you have half-life of what you started, right? So whatever the half-life period is, if we start with 5, it's gonna take us that long to get to 2.5, and then that long again to get to 1.25, and so on and so on. So when we're doing half-life, that's clearly an exponential relationship, because don't we just keep multiplying by a half, right? So we can write an equation for that, can't we? We can write an equation that says y equals, in this problem, 5, because what, and then 1/2 to the x. What does that 5 stand for in an
Initial value.
exponential? That's the initial value. That's what I'm starting with. I'm starting with 5. And then half-life means we're gonna keep multiplying by a half. So it says, find the time when there will be 1 gram remaining. So looking at the equation, obviously I'm gonna stick the 1 in somewhere. Where's the 1 gonna go? It's gonna go here. And what am I gonna do to solve that one? I'm gonna divide by 5. So I might just put 0.2, that's what 1/5 is. But it's up to you, you can use 1/5, it doesn't matter. So 0.2 equals 0.5 to the x. How do I solve that? I'm gonna log both sides, or ln, whatever flips your switch, won't matter one bit, no advantage either way. So log 0.2 equals x, log 0.5, because that comes out in front. And x is gonna be whatever the log of 0.2 divided by the log of 0.5 is. So, log 0.2 divided by log 0.5. Did you get 2.32? Now, we need to talk about that for a second. What does that 2.32 represent? How many half-lives there were? How many times we have? Well, each half-life is how many days? 20. So to get the amount of time that's elapsed, aren't we gonna take that times 20? And I'm not even gonna round it off, so I got 46.44 days. I didn't use that number, I used the whole decimal that was in my calculator, times it by 20, and there it goes. Everybody good with that? Now, number six, I'm gonna have you try that on your own. You already know how to do this, and it just takes too long, we have to do it in class. But this says, here's a data table. We're gonna use our calculator and exponential regression. So we're gonna put this into stat edit, right? And then we're gonna find, in our regression list, we're gonna find exponential, and we're gonna do it. A little hint, if you want,
Use the data.
you can call 1900 year 0, and then go from there, if you don't wanna keep putting in those great big giant numbers. All right, that's for your own time. Right now, we're going to the next problem. We'll talk about that if we need to. You guys are good with your calculator, so you'll be fine, I'm sure. We're going to number 7. You got 1,200 kids. Bob Carroll said, now let's start a rumor. Spreads logistically so that this, somebody's figured out that this equation models the number of students who have heard the rumor. So S of T is 1200 over 1 plus 39 e to the negative 0.9t. Now, first of all, did they need to tell me there were 1200 kids in the school?
No.
Doesn't the equation tell me that? Because what's the limit to growth? 1200. So so that tells me that's the rumor dies at that point. Everybody knows it. But anyhow, they told me, so here we go. How many students have heard the rumor by the end of day 0? Well, how would I figure that out?
Plug in 0 for T.
Yep, plug in 0 for T. That's easy. I didn't need a calculator, or maybe I don't know. If I put 0 in, doesn't this become 1? So isn't this just 1200 over 40? Is that 30? 30 kids? How long does it take for 1,000 students to hear the rumor? So here's our equation. What are we doing with the 1,000?
Put it for Y.
Put it in right here. That's like your Y value. So 1,000 equals 1200, 1 plus 39, e to the negative 0.9t. And we've done a couple of these already. All right, so what do we do to solve this?
Multiply by 1.
Multiply that over. So we're gonna have 1,000 plus 39,000 e to the negative 0.9t equal 1,200. And then, so 39,000 e to the negative 0.9t equals 200. And then, so e to the negative 0.9t equals 2 over 390. I'm just gonna leave it. I know it would be useless, but I'm gonna use my calculator anyway. And what? ln both sides, and this time you could log, but there's a definite advantage to ln'ing, because since there's an e, this side of the equation will just be negative 0.9t equal to ln 2 over 390. So I'm going to find ln 2 divided by 390, and then divide that by negative 0.9. Wow. I got 5.86 days. So it doesn't take long, does it? Got it? Okay. Well, in all of our logistic problems so far, we've been given the equation, and then we just plug stuff into it to figure stuff out. Next little problem here is having us write our own logistic function. So we're only going to do one of these, either A or B, I don't care which one. I guess we'll just do A. It says write the logistic function given the initial value is 10, the limit to growth is 40, and f of 1 is 20. Now remember, this is just a point, right? That's just a function notation for a point. So they've given you your initial value, which by the way is your y-intercept, right? they've given you your limit to growth, which in a logistic function is the
Top number.
numerator, and they've given you some random point. Okay? Now, the format we're gonna use, and you can use other formats, but we are gonna use this format for our logistic functions. So think about the equation I just erased. I'll scribble it back up here real quick. See that format there? Got a number and then 1 plus some thing here, and then a base, which was E there here, I'm just calling it C, and then an exponent of some kind. All right, so here we go. Is there anything I can fill in right now before I do anything else? Notice there are 3 numbers I'm responsible for finding. Do I know any of those?
You know,
I know it. So right off the bat, I can plug in a 40 over 1 plus b times c to the x. Done deal.
Wait, so in this, A isn't your initial value, it's your limit to growth?
That numerator, whatever you call it, I don't care if you call it A, you can call it whatever you want, that's your limit to growth, yes.
Is B 3?
Is B
3,
3? How did you get B to be 3?
because if it's initial, x is 0.
What?
If it's initial, x is 0.
So, I'd have to figure it out, Zoe, you're ahead of me here, but Zoe said the initial value is the y-intercept. So that means if we plug in 0 for x, we should get 10? Doesn't that make sense, kids? Initial means beginning, so we're gonna let x be 0. So if we put in a 0, we're gonna have 40 over 1 plus bc to the 0th, and that has to equal 10. This is the point 0, 10. So if x is 0, y has to be 10. Now, at first glance, that's scary, but what's this?
1.
That's 1. So this is really just 10 equals 40 over 1 plus b? Zoe said b's gotta be 3. Well, we can solve that or just use our brilliance like Zoe did. We have 10 plus 10b equal to 40. So 10b equals 30 and b equals 3. So now, we go back to our original framework here. Now we have 40 over 1 plus 3 b to the x. Or not b, c to the x, sorry. I know b is 3.
Then could you plug in your point?
Exactly. Remember, they gave me another random point, so I'm gonna plug that in.
Could you not plug 10 in for C? Because I know in the exponential one, C usually means our initial, or, wait, no, that's the X, never mind.
Okay, so I mean, I don't know what C is gonna turn out to be, but I'm going to do exactly what they said. This is a point right here, so 20 equals 40 over 1 plus 3c to the first. So 20 plus 60c equals 40. C equals 20 and C equals 1/3. So then our final answer, the equation, is y equals 3 1/3 to the x. Lucy?
So is there not gonna be an e in this equation at all?
Not the way I set it up. I use c as my base,
Okay.
okay? That made it easier.
How would you know?
You can, we don't care what the base is, you can use whatever base you want. So I'm setting up this way. Every time I write a logistic function, that's the setup I'm using. Just like every time I do an exponential, I use this. Could the base be e? Yeah. I'm not setting it up that way, but it could be.
Are there gonna be logistic functions where it's not a 1, but it's a 2, or it's like a 0?
That won't matter. That would just mean you'd have to be square rooting to get your answer. Right? Or whatever power it is.
Well, I mean, for the bottom number, for the denominator,
Like the 1.
the 1 plus
Now,
BC.
remember, my job was to write a logistic equation, and I said that's the format I am using. So no, I'm not gonna set them up that way. Could I? Probably, but they're not normally that way, so I'm not going to.
Okay.
You can set it up however you want. My suggestion is you use this format. Just like my suggestion for exponential says use this format. All right. Let's at least write the equation for number 9. Number 9. This one's exponential. Alright, so I just erased it, but we're gonna write an equation that looks something like y equals a times e to the x. So let's see, in number 9, what can I put in?
4,200.
4,200 will be my a. Now, the minute I do that, I've now defined x. What is x gonna be? Years, cents, 1910? Which is fine, just keep that in mind. So when you get an answer like 12, that would mean 1922, right? Okay, yep, I would do that definitely. Okay, then what?
1, your base, 140, 235.
Beautiful, beautiful. There's your equation. So when it says, estimate the population in 1930, what will you put in for x? 20? Yep, type it in, get the answer. Done. Predict when the population reached 20,000. What would you do then? You would put 20,000 here.
So B.
Let's solve this one. What would you do first to solve this? This is, we're predicting when the population reaches 20,000.
Divide by
So
4,200.
we're gonna divide, so I've got 200 over 42. And again, I know that reduces, but I can reduce it if you want. Go ahead and reduce it. I'm just gonna leave it be because I know the next step is going to be to use my calculator, right? So I'm gonna log both sides. So the log of that fraction, in whatever form I've written it, is x times the log of 1.0225. So the log of 200 divided by 42 divided by the log of 1.0225. Did you get 70.14? So how are we gonna answer the question? Please don't say 70.14. Early in 1980? Because we started counting in 19. like you go back to your BFFs for a minute. By the way, 3.2, let's have that due on Monday. We have office hours tomorrow and Monday. So if, by chance, you know, I skipped a few problems there, I'm having you do some more graphing on your, regression on your calculator. If there's something there you got a question about, you know where to find me. And now we're gonna answer this question, what the heck is a logarithm? We know what we use it for, and we know they're incredibly handy and powerful. What is it? Well, let's look at these two BFFs. We've talked a lot about that one. It has an intercept at 0, 1, and an asymptote at y equals 0, and it looks like that. Right? Now, on the same axis system now, I can graph ln x. Now, what do you remember about a logarithm picture? What do you remember about it?
The root at 1.
Okay, so it has an asymptote at x equals 0, contains the point 1, 0, and does this. Now, just for the fun of it, I'm going to sketch in my identity line. What do you notice about the relationship of the black, the pink, and the purple?
It's symmetrical about y to x.
So, yes. So these are mirror images of each other across the identity. This one contained the point 0, 1 and had an asymptote y equals 0. This one contains 1, 0, has an asymptote x equals 0. The exponential function and the logarithmic functions are inverses of each other. Isn't that what happens with inverses? Don't we switch the ordered pairs? They're reflections across the identity line. So what is a logarithmic function? It is the inverse of the exponential function. Now I want you to think about it for a second. You think, okay, why did they do this whole logarithm thing then? Why can't we just think of it as an inverse? Well, let's not use E, let's use 2. Would you agree with me that the inverse of that would be x equals 2 to the y? But mathematicians like to use function notation. Both the black and the purple are functions, right? So I have no problem writing this one as y equals 2 to the x, but then this one would have to be x equals 2 to the y. Now just think about your calculator. Could you type that in on your calculator? No, when you put something in to draw a picture of it, it has to be y equals. It has to be function mode. So what are you going to do to this equation to get y equals?
Log.
Yeah, exactly. The only way to get that y by itself is to put a logarithm into this problem, because that will pull the exponent off. The logarithmic notation wasn't something that was just made up to make your life miserable. It was some really smart guy said, okay, I need a new notation and I'm going to use the logarithm notation. He could have made it some other word, but you need a new notation to get that exponent down so that you can graph that. Think of it as a function. Graph it on our calculator, write it in terms of function notation, all that stuff. The logarithmic function is simply the inverse of the exponential. Okay? All right, so let's do some work here. The most important thing that I have said to you all week will say to you all week, the most important thing is, if you have something that looks like this, y equals b to the x, that's an exponential. That is the same and can be written as log base b of y equals x. These two things are exactly the same. Mr. Miller, didn't he call it log rolling or something? B to the x equals y, something like that. I never did figure it out, but that's what he did. These two things are exactly the same. So when I look at a problem that said the log base b of 1 equals 0, what that really says to me is b to the 0 equals 1. B to the 0 equals 1. So one of your properties of logarithms is, if you take the logarithm of 1, you get 0. Well, that makes sense, but it makes sense from the picture too. If x is 1, isn't y 0 on your logarithmic curve? Yeah. So I got a whole bunch of properties listed there, basic properties of logarithms. You need to know those properties, but if you understand this concept right here, if these two are equal both ways, these are equal, then these properties aren't going to be a problem for you. You're going to understand them perfectly. So, if you don't already know them, spend some time with them. Make sure you're comfortable so that when I give you a problem like 11 to the log base 11 of 6, you will say, oh, 11 to the log base 11 of 6 is 6. That's one of your properties. Maren?
Can you go through like the example of like how you would get b to the y equals x from y equals log b to the x? Like how do you go from one to the other?
You mean up here?
I think she's talking about that.
Yeah, like the example under like logarithm.
Okay, I just did that here. Okay, I mean this would be a property with numbers in it instead of letters. Okay, so let's take the logarithm of those sides. Now that'll pull the exponent off. So I have log base 11 of 6 equals log base. Oh, I should have taken the log base 11, sorry. I need to use the same base. So I'm going to take the log base 11 of both sides, pull the exponent off, so the log base 11 of 6 times the log base 11 of 11 equals the log base 11 of 6. So I had my original statement, the property you're asking me about, I put numbers in it. Took the logarithm of both sides, which I'm allowed to do, use the same base so that everything matches up, pulled the exponent off, so now it's out here. So now I have the log base 11 of 6 times the log base 11 of 11 equal to the log base 11 of 6. Now, what's this?
1.
That's 1. So doesn't that make sense?
No.
Well,
Like
that's
that, no,
one.
that makes sense, like 11 to the first power would equal 1 by.
Let me try one more time and then we gotta move on. So, I'll try one more time here. So, your question is, how do I simplify? So let me say, let me just call it.
Well, I'm just looking at like the example up here, like y equals log base b of x. Like how you can get b to the y equals x from that. Like how is that the inverse?
Okay, that is not the inverse. Those are equal relationships. The inverse of this would be x equals b to the y. which would look different when I changed it into its logarithmic form. All we're doing in that problem is showing you that every exponent can be rewritten in a logarithmic form, and every logarithmic form can be rewritten as an exponent. I am rewriting the expression. I'm not taking the inverse, finding the inverse. I'm simply rewriting it. You gotta memorize that this and this are the same. Those are exactly the same. Different ways of writing the exact same equation. They aren't inverses. They are the same equation. Okay? Because somebody's gonna wanna know, what's the log base 5 of 25? What's that equal? And you're gonna say, well, this is the equivalent of 5 to the x equals 25. So the log base 5 of 25 is 2. Because you're gonna probably wanna rewrite that as an exponential. Because most of us think better in terms of exponents than we do in logarithms. So you're gonna memorize this. You're gonna memorize that those two things are the same. Okay? Alright. So let's do some without a calculator. So 1a. What's 1a going to be? Log base 2 of 8. What's that gonna equal?
3.
So you can either think of it as 2 to the x equals 8, or you can think of it as the log base 2 of 2 cubed. And you have a property that says the log base 2 of 2 cubed is 3. In general, you know how your e's cancel when you did ln and e? In general, if the base of the logarithm and the base of the exponent are the same, they're gonna cancel because they're inverses of each other. So when you put them in the same equation, they cancel out. It's like a multiplication and a division. They cancel. So you think of it either way. 2 to the x equals 8, or the log base 2 of 2 cubed. Either way, the answer works out to be 3. What about b?
1/3.
No, not 1/3, I don't
1/2.
think. The log base 3 of 3 to the 1/2 would be 1/2, wouldn't it?
-2.
What?
I'm on problem B. I have no idea where the
I didn't see, that's what I'm saying.
Okay, so let's all look at B. Are we comfortable with 1/2 now that we're looking at the right problem?
Yeah.
3, or the square root of 3 is 3 to the 1/2. All right, now C, this is where some of you were saying negative, because we have the log base 5 of 5 to the -2nd. So the answer to C is -2. It is -2. How about D? 0. Log of 1 is 0. E, 1. And F, 11. Now, I hear people saying what? You need to look up at your list here, and you need to figure those out. You need to know those. Those are properties, they're called basic properties. If we're gonna talk about logarithms, we need to know those basic things. Common versus natural logarithms. Anybody know the difference? Common logs and natural logs. They have exactly the same properties, so it's not like there's a separate list for each. A logarithm is a logarithm, no matter what the base. We have base 7 logarithms, we have base 39 logarithms, that's not important. The two most common logs and natural logs. Common logs are base 10. they are so common that we don't even see the base. They don't even write the base, they just write LOG. When you have an LOG symbol, that means your base is 10. So when somebody says log x equals 2, the base on that is a 10. 10 to the second is x, so the log of 100 is 2. Any idea why base 10 would be the common log?
Scientific notation.
Well, okay, and what, it definitely is tied to scientific notation, but why is scientific notation 10 to a power? Because that's our number system, right? Don't we have 10 digits in our number system? We have 0 through 9, and then every number we build that's bigger than 9 is some combination of 0 to 9. And it's all based on powers of 10. Your tens digit is 10 to the first, your hundreds digit is 10 to the second, and so on. Logarithms were originally invented, originally created to help with computation, because there weren't calculators. So if you had to multiply two big numbers, think about it. If you had to multiply two big numbers, could you write those numbers in scientific notation and make them smaller? Yeah. And then, if you were multiplying them, and this one was 10 to the 5th, and this was 10 to the 2nd, what would you do with those exponents? Just add them. So a big, hard, long problem turned into a much easier problem by changing them into scientific notation. And then the logarithms would help you with the actual computation. If we have time, I'll bring in a log table and we'll see how that works, because it's really quite cool. That Napier guy, the guy that wrote about all that originally, he's pretty sharp. Okay, what about natural logs? What are natural logs?
ln.
Well, they are log base e, and their symbol is ln. Everything you can do with a common log, you can do with a natural log. Properties are the same. So if somebody says, ln e to the 7th is what? Well, remember, the base on that is e. So you can either cancel those out, which is what we've been doing in our equations that we're solving, or you can say e to the x equals e to the 7th, so clearly x is 7. All the properties are the same. Now, it's been a long time ago, maybe, I don't know, time is on many years ago, I was reading an article, and it said that my children, so it didn't work out this way, but the supposition was that children in the next generation, which would be my children, a little bit older than you, would have another logarithm they would study, and it would be the base 2 logarithms. Now, we can do base 2 logarithms, because you can do base anything logarithms, but anybody have an idea why this article said base 2 logarithms were going to become so important?
Does that have to do with even numbers?
What?
Even numbers?
No, it doesn't have anything to do with even numbers.
It was a good guess. It was a
It was a good guess, yeah. Our guesses are good. When a computer operates,
Oh yeah, because the computer.
when a computer operates, it's all zeros and ones. It's on and off, right? So it operates with a base 2 number system. In a base 2 number system, you have zeros and ones. That's all you've got. So this article was saying our society is becoming so computer oriented that pretty soon all of our math will be in base 2. Well, that hasn't worked out yet. Maybe it will in the future. But anyway, we could do base 2, we just don't. We could. All right, let's do a couple problems though. How about, I'm now down on number 2, clear at the bottom. Any idea what ln root e is? 1/2. What's the log of 100? 2, because 100 is 10 squared. What's 10 to the log 6? 6, because the base on that log is 10, so it's 10 to the log base 10 of 6. How about D?
5.
5. How about E? 4. Whenever you have that ln and that E, right, touching each other, they're going to cancel out because they're inverses. All right, what's that? -3. Why is it -3?
Because 10 to the
Because 1 over 1,000 is 10 to the -3rd. So the log base 10 of 10 to the -3rd is going to be -3. And what about G? 1/5. 1/5. Because the fifth root is a 1/5 power. Very, very good. All right, get out your calculator, type in log 34.5. No, there is nothing special about 34.5. I made that number up. I want you to tell me though, you took the log of 34.5, and did you get 1.538? So it says, what does that number mean? What does that 1.538 stand for?
10 to that power.
Exactly. So when you did log, you did base 10. So 10 to the 1.538 power equals 34.5. So basically, the value of that logarithm is the power on 10 that generates the number that you're interested in. All right, so you could do ln 1/19th, right? You could do ln 100, right? Try log -3. No, try it.
It
What
doesn't
happens?
work.
It doesn't work. Let me go back. This is our logarithmic BFF. Right there, he is. What did we say the domain is? This is the equation y equals ln x, or basically y equals log base b of x. Or the one we memorized was ln, but it's any base, okay? So tell me about the domain of this problem. What's the domain? Greater than 0. So that means whatever you put here for x has to be bigger than 0. You cannot take the logarithm of a negative number. It will never work.
Would it be imaginary?
What?
Could it be imaginary?
Some people talk about imaginary, but then you're not on this graph anymore, so we're not gonna go there. No solution, can't be done. Now, I want you to remember that, because in a minute here, well, these are sketches, but at some point soon, we're gonna be solving logarithmic equations. Okay, so we're gonna get answers like x equals whatever. Make sure you're paying attention, because you can't take the logarithm of a negative, so some of those answers are going to have to be discarded. Okay? You cannot ever take the logarithm of a negative. All right, sketch with no calculator. Please keep in mind that this curve that we've been talking about with an asymptote at 0 and an intercept at 1, 0, that is the logarithmic picture. The base does not have to be anything particular. This is a logarithmic curve.
Is there a difference between the curve for log and natural log?
No, that's what I'm just saying. Now, okay, let me back up. Yes,
Like the shape.
the general shape, no. Every logarithm is gonna have this shape. It's gonna have an asymptote here, it's gonna have a point here, and then the actual curvature will vary depending on the base, but this is gonna be the shape of it, right here. Okay? So what happens when we do ln x plus 2.
You shift it 2 to the left.
You are gonna shift it 2 units to the left. So instead of the asymptote being at x equals 0, it's now gonna be at x equals -2. And instead of the intercept being at 1, 0, it's now gonna be at -1, 0. Now that won't change the range of the problem, because it's still going down and up, but that will change the domain. What's your domain for now this function?
-2 to infinity.
Right. So, again, I don't wanna be a dead horse here, but you didn't hear Mrs. Ford say x can't be negative. You heard me say you can't take the logarithm of a negative number. So in this case, could x be -1?
Yes.
Absolutely, because then I would be taking the log of a positive. X couldn't be -3, because then I'd be taking the log of a negative. That's the key. It's not the x value, it's what you take the logarithm of. Okay, how about b? What's b gonna look like?
Translated out.
It's gonna take this curve right here and pick it up 1. Is it gonna change the asymptote? No, it's gonna make this point now is gonna be 1, 1. And it's gonna just be raised up 1.
You're not allowed to take the log of 0.
No, because, think about that for a second. I'll just use base 10. Oh wait, the log is 0. Let's see what happens here. So I'll just use base 10. If we change this to its exponent form, Oliver, what's it say?
10 to the x equals 0.
Can you raise 10 to a power and get 0?
I don't think so.
No, you can't, right? So, no.
You get really close.
You get really close, but you can't get there. So no, you can't take the log of 0, it's an asymptote. All right, how about C? C, two things are happening to it. I'm gonna go ahead and sketch my original here. All right, so what's happening in letter C? It's reflecting this way?
Why?
No, it's reflecting upside down. For C. A negative out in front goes upside down. Where does, how do you get a reflection this way?
Inside
Change
the
the sign on
parentheses.
X. You gotta change the sign on X. So this is gonna go upside down. And what else? To move right 1. So I'm gonna go ahead and do that first. I'm gonna go ahead and move it. So I've got my asymptote now at 1 and my intercept at 2, 0. So would you agree this is a picture of ln x minus 1? So now I gotta make it negative, which means turn it upside down. Like the purple? Now some of you, I can tell by looking at, you're doubting me. Let's graph this on our calculator and see. So, I don't know what window you've got, but let's just use a standard, because we don't need some weird window. And just graph y equals negative ln x minus 1. You get something that looks like the purple or the pink one I've got here?
Mine is cut off a little bit.
I know, and I don't get that. I know there's a reason for it. I don't know what it is.
It's just, oh, yours too. Because why can't
Now, what about D, you guys? What about D?
It just reflects over the Y.
D is gonna take that picture right there, the original, and reflect it how? Across the Y. So instead of 1, 0, it's negative 1, 0. And it looks like this. Everybody okay with that? E is a really tricky problem. So I'm gonna send you out with 2 things that I want you to do on your own, okay? I want you to do that exponential regression problem. Type in those things and see if you can get the exponential. And then I want you to play around with E using your calculator. Let your calculator help you and see if you can figure out how we would sketch that by hand. Because it may not be exactly what you expect. It's a little bit tricky. So I'm gonna have you do those 2 things on your own. And we will pick up there next time. So see if you can figure out what's happening in that problem, how things are getting moved